Welcome. In this video, we talk about polynomial and rational functions, and we are in day 2, properties of rational functions. Now, this is section 5.3 from the book, and we will cover all 3 objectives. Let's go. So what is a rational function? Let me just show you a bunch of examples. So here on the left, you can see rational functions are functions that have the form polynomial divided by polynomial. And sometimes the polynomial might be totally expanded out, like in example h, or the polynomial might be factored on top and factored on the bottom, like in example f. But either way, it's a polynomial divided by a polynomial. That's exactly what makes a rational function. And on the right, you can see some pictures of these things. Basically, they look like collections of curves. They tend to be kind of broken up. So not like a polynomial, which is nice and smooth. Rational functions consist of several parts. The domain of a rational function. Well, it turns out that a rational function is defined for all x values except those x values that make the denominator 0. So let's take each of these 3 examples and we'll figure out what their domains are. So how about this first one, q of x? To find those values that are not in the domain, I figure out where the denominator is 0. So I want to solve 3x squared plus 5x minus 2 equals 0. Now, this one might take a little bit of time, but I've worked it out already, and it really does factor. In fact, do you see how it factors? There's a 3x and an x, and then a 2 and a 1. Can you see how it goes now? To get the 5, I need to do a 6 minus 1. So I'll do a plus 2 and minus 1 there. All right, we're getting closer. Now, what are the x values that make each of these factors 0? Well, the right one is easy. That's just x equals negative 2. But what about on the left? 3x minus 1 equals 0? Yeah, think about it for a little bit. It turns out x equals 1/3. So the domain of q of x is all real numbers except 1/3 and negative 2. Let's try the h function. What is the domain of h? Well, I need to solve, in order to figure out the numbers that are not in the domain, solve x squared plus 9 equals 0. All right, so I figure x squared equals negative 9, and oh, look at that, x squared is always 0 or positive, so there's no solution. So in fact, every real number is in the domain of h. And for my third example, how about f? What is the domain of f? All real numbers except where the denominator is 0, so let's solve. And that factors. So the solution to this equation is simply x equals negative 2. So that's the only point that is not in the domain of f. So the domain of f is all real numbers except negative 2. Transformations. 2 of the most basic rational functions are just 1 over x and 1 over x squared. And you can see their graphs here. And try to plot a few points to convince yourself that these are really the correct graphs. Well, we can do transformations of these to get a lot of basic rational functions that we see often. Here's some examples. How would I graph 1 over x minus 3? Or how would I graph negative 1 over x plus 2 squared? So we can do some transformations. I might start with 1 over x for this guy on top. And 1 over x, here we go, is simply something like that, roughly. And now, how do I transform it into 1 over x minus 3? I'm subtracting 3 from the x, which means I need to shift right 3 units. All right, so I'll make my axes. So I'm going to make a little dashed line, 1, 2, 3. That's 3 units to the right, and this will help guide me. And now my new graph uses that dashed line. There we go, something like that. How about the next example? Graph negative 1 over x plus 2 squared. So it looks like I'm going to start with the 1 over x squared graph. And then from there, let's make 1 over x plus 2 squared. So I'm getting closer, so I need to shift to the left 2 units. So I'll make some axes. I'll go to the left 2 units, make my dashed line, so everything gets shifted over to the left like that. And then the last step is to negate the whole thing. And what does it do to a function if I negate the entire function? It just flips it over vertically. All right. So it's shifted over, and now flip it. There we go. That's what the graph will look like, roughly. Let's talk about asymptotes. The graph of a rational function has several parts that are broken up, but between those parts there are often lines that the graph approaches, and that's what an asymptote is. An asymptote is a line that the graph approaches but never crosses. And there are three kinds of asymptotes. There are vertical, horizontal, and oblique asymptotes. The first example on the left here, this shows a graph that has a vertical asymptote and a horizontal asymptote. So the vertical asymptote, let's see, that one occurs here. So VA, vertical asymptote at, now what is the actual equation for that line? That's x equals 2. And it has a horizontal asymptote at, so this nice horizontal line. So as the function goes infinitely to the left or infinitely to the right, its y values are approaching y equals 1. So it has a horizontal asymptote at y equals 1. The next graph, this has two vertical asymptotes. So the VA is vertical asymptotes at x equals -2 and x equals +2. And it looks like it has a horizontal asymptote at y equals 1. Now this third case, this is interesting. This is called an oblique asymptote. The line that this approaches isn't x equals a number or y equals a number. It's the equation of a line that's slanted. And so in this case, the equation for that dashed line is actually y equals -x. So we'll see in a little bit how to figure out the equation of the line that is a slope asymptote. All right, and then I guess in this last example, the vertical asymptote at x equals -1, and it has a horizontal asymptote at 0. It might be a little hard to see, but it's actually the x-axis itself that's acting as the asymptote. And that equation is y equals 0 for the x-axis. All right, let's see how we can actually figure out what the asymptotes are. So finding vertical asymptotes. Take our rational function r of x, and we're going to write this p of x over q of x in lowest terms, so that p of x and q of x have no common factors. Then the vertical asymptotes occur where the denominator is 0, kind of like the calculation we did when we were figuring out domain. The numbers that aren't in the domain, that's where the vertical asymptote occurs. But again, this is after reducing, so putting things into lowest terms. Let's see how this works. Find the vertical asymptotes of these two things. So on the left, I'll factor it out, and I get, this is the same as x over x plus 5, x minus 5. And I need to ask, is there any reduction that I can do, any canceling of factors? No, there isn't. This is in lowest terms. So this has vertical asymptotes at -5 and at +5. How about this next example, g of x? Again, let's factor the top and the bottom. All right, so I've factored the top and I've factored the bottom, and it does look like there's a common factor here. Now, 3 is definitely not in the domain of this function, but it's also not where a vertical asymptote occurs. In fact, since the same factor appears on the bottom and the top, there's just a little hole in the graph. But anyway, I cancel those out, and now what remains, this x plus 7, that tells me where there's a vertical asymptote. So it looks like there's a vertical asymptote at x equals -7. There you go, and that's how you figure out where your vertical asymptotes occur. But what kind of vertical asymptote is it? You can see sometimes you have a vertical asymptote where the graph splits in different directions. And sometimes you have a vertical asymptote where the graph stays on the same side. Well, it turns out that I can analyze the multiplicity of the 0 in the denominator to figure out how the graph behaves around the asymptote. Here it is. You can determine how a function behaves around a vertical asymptote by looking at the multiplicity of the 0 in the denominator. Okay, so what do I mean by that? Here we go. In this example on the left, I definitely have asymptotes at 1 and -3. And this asymptote at 1, that occurs with multiplicity 1, and at -3 with multiplicity 1. So both of these split. The graph splits across both. And that's the example I have up there. Now, I don't really know which side is up and which side is down. A little bit more analysis is needed, but at least I do know that the graph will split in opposite directions. Now, this example on the right, let's see, does that numerator factor? No, it doesn't. So this is already in factored form, which is good. There's an asymptote at x equals 2, and this has multiplicity 4. So since it has even multiplicity, I know that the asymptote at 2 behaves so that the curve is in the same direction on both sides of it. Now, at 5, there's another asymptote which has odd multiplicity, so the graph will split around there. And once again, I don't really know which side it stays on or in which direction it splits. I'd have to do some further analysis before I can determine that. Well, let's talk about horizontal asymptotes. The idea is to analyze the end behavior of the rational function. A horizontal asymptote is really asking what goes on when x is really, really big, positive, or really, really low, negative. In this first example, you can see as x gets really big, positive, my y values approach positive 1. And same thing here, as my x gets really low, negative, those y values approach positive 1. So finding a horizontal asymptote is really equivalent to figuring out the end behavior of this rational function. That numerator, let's suppose that that has leading term, a times x to the n. And the denominator, let's call that a leading term, b times x to the m. For example, in this rational function, the leading term on top is 8x to the 5th. So that's like my ax to the n. And the leading term on the bottom is 2x to the 5th. So that's my bx to the m. Now, the key idea behind analyzing rational functions is that the end behavior of the rational function is the same as the end behavior of ax to the n over bx to the m. So by analyzing this guy, I know the end behavior of my rational function. Maybe you can recall, this is pretty similar to how we analyze polynomials. With polynomials, when I wanted to know the end behavior, I looked at the leading term, and I asked, what is the end behavior of that leading term? So we do something similar, but I'm taking the ratio of the leading terms of the two polynomials. Okay, here are the rules in general. So let's consider this ratio of leading terms. If n is less than m, the power of the numerator is less than the power of the denominator, then my rational function has horizontal asymptote y equals 0. So it's this kind of a situation. The x-axis is acting as the horizontal asymptote. We can see here in this example I have 8x to the 5 divided by 2x to the 7. And so since the bottom power is bigger, it overpowers the top, and it goes to 0 as x gets really large. You might be able to see this better if I cancel out some x's. So this becomes 8 over 2x squared. So now you can think as x gets really, really big, or really, really low negative, this denominator gets huge. And so the whole fraction goes to 0. The next case, n equals m. So the power of x in the numerator is the same as the power of x in the denominator. Then my rational function has a horizontal asymptote y equals a over b. So for example, in this case, I have 8x to the 5th over 2x to the 5th. The x's cancel completely. I have 8 over 2, which is 4. And so I have a horizontal asymptote at y equals 4. Now, the third case is when I don't have a horizontal asymptote. If my power of the numerator is 1 more than the power of the denominator, then my rational function has an oblique asymptote. And it's important, it has to be just 1 more. So in this example, we can analyze 8x to the 6 and 2x to the 5. 6 is 1 more than 5, so I know there's going to be an oblique asymptote. So now the question is, how do I find that oblique asymptote? All right, let's take a look at that. So it's definitely a little bit more of a process to figuring out the oblique asymptote, but it's not bad. So just several steps, but all the steps are pretty easy. So here's what we do. Step number 1, chop. Oh, you can see the overall strategy on the right. Chop, cancel, multiply by conjugate, chop, cancel. So 5 steps, but they're all easy. So let's see what we can do here. Chop. So what do I mean by chop? What I do is I'm going to remove everything after the top 2 terms. I just chop them off. And so I end up 8x to the 6 minus 9x to the 5 divided by 2x to the 5th minus x to the 4. It's a little bit like just looking at the leading term, removing everything except for the leading term to know end behavior. But I need just a little bit more information than the leading term. I need the leading term and the one that's 1 power less. So you see how I have x to the 6, then I need to also know the x to the 5 as well. And that will give me enough information to find the whole line of the slant asymptote, the oblique asymptote. All right, so I've chopped off everything except for the top 2 terms. Now, cancel. Basically, I have a bunch of x's in there. Let's cancel it out. Now, the smallest power of x is x to the 4. So I should be able to take away x to the 4 from everything. And here we go. So that x to the 6 turns into x squared. X to the 5 becomes an x. X to the 5 becomes an x. And x to the 4 becomes a 1. So I've taken out x to the 4 out of everything, just to make it a little bit simpler. Now this is the trickiest of all the steps. Multiply by the conjugate. What do I mean by that? Look at your denominator, 2x minus 1. There's an expression called the conjugate, which is 2x plus 1. And what I'm going to do is multiply the top and the bottom by 2x plus 1 over 2x plus 1. So here we go. So I've taken my original fraction, multiply the top and the bottom by 2x plus 1, and since I multiply the top and the bottom by this thing, I'm not really changing the problem. But this does something nice to the form of the function. So in the denominator, I end up with 4x squared minus 1. In the numerator, I did FOIL, so you ought to check my work on that. You do FOIL and you end up with this polynomial. Well, now I have something that has gotten a little bit more complicated. Well, I can do my chop and cancel steps again. So my top 2 terms here are x cubed and x squared, and so I will chop away the negative 9x, that doesn't matter. And on the bottom, the top 2 terms ought to be 4x squared, and if there's an x, so sort of like a plus 0x. And so after chopping, I get 16x cubed minus 10x squared just over 4x squared. Since there's no actual x term, it just stays the 4x squared. And now I can cancel my x's again. So I have, looks like x squared that was able to go away. And now, let's see here, I'll just reduce this. This becomes 16x over 4 minus 10 over 4, and that's 4x minus 5 halves. So that, there we go, done. That actually becomes the answer. That is the line that is my oblique asymptote. So it's really kind of a curious process, right? Chop, cancel, multiply by the conjugate of the denominator, chop and then cancel, and then you'll be done. After that process, you will have your answer. Let's do one more example, and in fact, I'll invite you to pause the video and give this thing a try. The one warning I might say at the beginning of this is look carefully at the top. When you do your first chop step, you don't take 5x to the 8 minus 9x to the 5, because you really want an x to the 8 and an x to the 7 power. So you won't have those two things. What will you have? Okay, pause the video, give this thing a try, and then start it up again to check your work. Let's take a look. All right, there's all the answers at once. When I chopped, there was no x to the 7 term, so in fact everything went away, and I have my x to the 7 and x to the 6 terms down below. I canceled out my x's, and so I was left with 5x squared over x minus 3. Then this x minus 3 has a conjugate of x plus 3. So I multiply the top and the bottom by x plus 3. Then using FOIL, the denominator becomes x squared minus 9. The numerator, actually I don't need FOIL for the numerator. I just distribute 5x squared. I get 5x cubed plus 15x squared. And then I can chop again, and it looks like the 9 goes away. And now I can cancel x's, and I'm left with 5x plus 15, and we're done. 5x plus 15 is the line that is our oblique asymptote. All right, and there you have it, properties of rational functions.